All right, so we're going to start Unit 5 today, and Unit 5 is all about chemical bonds. So we've talked about a bunch of stuff up to this point, letting us understand how the atom works and where the electrons are in the atom and what else is in the atom and all that good stuff. And it's all leading us up to this, chemical bonds, talking about how the atoms react with one another. We'll get into this, and then once we get into chemical bonds, we learn about chemical bonds, then we can begin to learn about, they kind of extend that out a little bit more to learn about compound naming, how to name formulas, and then reactions, and when you mix this with this, what kind of reaction takes place and what kind of results you get and that sort of thing. But for the next little bit, for the next few weeks, we're going to be just talking about chemical bonds. So this is chapter 6 in your textbook. So I know it's unit 5, I know that's crazy and all that good stuff, but it's chapter 6 in your textbook. We will go over almost all of chapter 6 in the textbook. The first part of section 5 in the textbook is on molecular geometry. That part's not in our standards. We don't have to cover that part. So we will not include that part. I think it's page like 197 to 202, or actually just a little bit at the top of page 203, that we won't cover it all. The rest of chapter 6 we will cover in this unit 5 here. So, all right, chemical bonds. A chemical bond is a mutual electrical attraction between the nuclei and the valence electrons of different atoms that binds the atom together. So it's the nucleus of one atom and then the valence electrons, those outer shell electrons of another atom that are attracted to each other. So the electrons are negatively charged, the nuclei is positively charged. So of course that opposite attraction, they're attracting to each other and they're coming together, right? So the valence electron of one electron and the nucleus of the other. Now if that's happening with one, then the opposite, this atom over here, its valence electron would also be attracted to the nucleus of this atom, right? So and that energy of electrical attraction there is what's binding them or holding them together. I told you this, guys, before. I'll say it again. An atom, they're selfish. They're only going to do things for their own personal gain, only what they're going to get out of it. It's not benefiting them to get in a bond. They're not going to get in a bond. Okay. So what does it mean to benefit them to get in a bond? Okay. And atoms bond together in order to do two things. Number one, to lower their potential energy, and number two, to become more stable. Okay. If it doesn't lower their potential energy and make them more stable, then they're not interested in getting in the bond. They will not bond. So some things, we'll take, potassium. Potassium bonds with a lot of stuff, and it likes to bond because it really has one valence electron. It really likes to lose that valence electron, so it is very active in the bonding. Okay, if you take something like I don't know, let's say zinc. Zinc's not going to be quite as active in the bonding process. So it still bonds with stuff, but it's a little bit more picky in when it's going to get in a bond than, say, potassium is. Potassium is a little bit more eager to get in a bond, so it's going to bond with more things. Okay? Regardless, across the board, they're going to do it to lower their potential energy and become more stable. Those two things, you'll hear me say it over and over again. Lower their potential energy and become more stable. All right? So there's 3 types of bonds that we would talk about. We would talk about ionic bonding. We would talk about covalent or molecular bonding. If you covalent bonding, molecular bonding, same thing. Okay, two different terms that mean the same thing. And then a little bit we'll talk about ionic bonding. Just a tad bit we'll talk about ionic bonding. So not ionic bonding, excuse me, metallic bonding. So ionic bonding, molecular / covalent bonding, and then metallic bonding. Okay, and then the covalent bonding will actually break up into kind of subdivide that again. So first, ionic bonding. Ionic bonding is the result of electrical attraction between the cations and the anions. So cations we know are positively charged ions. Remember, an ion is just simply an atom or a group of atoms with a charge. So a cation is a group of atoms or an atom that has a positive charge. That means in order to have a positive charge that they've given up an electron, and that difference in charge, because they've lost an electron, now they have more positives than they do negatives. So they are, as a whole, positively charged, right? Metals tend to be cations, okay? We talked about this in the last unit on the periodic trends, but metals tend to be cations. Anions are negatively charged ions, okay? Same thing, but that means they've added an electron, and that additional electron gives them more negatives than positives, so their overall charge is negative. And when you get a cation and an anion together, because one of them's positively charged, one of them's negatively charged, they are attracted to each other because of the difference in charge there, right? Produced by gaining electrons, like we said, they add another electron, and nonmetals are the ones that tend to be anions. All right, so that's that's ionic bonding, basics of that. This is just a little picture to kind of give you an idea of what that looks like. This would be your common table salt, sodium chloride. So you have, if you can see, and I'm sharing the slides with you, so just like I always share the slides with you, you can go and you can look at the individual slides, not just the video of me talking about this. But you can see sodium, and then you can see all of its electrons, and you can see that in this outer shell, valence electron, there's only one electron there. So sodium only has one valence electron. On the other hand, if you look at chlorine, here's all, it's got 2 in the first level, it's got 8 in the next level, and then it's beginning to fill up the third level, but it's actually, this one's not, oops, I got too close. This one's not here yet, okay? They're showing this guy leaving and coming together. So it really only has 7 in that outer shell right now, which we know chlorine is a halogen, it's group 17. Group 17 has 7 valence electrons, right? This guy's group 1. Group 1 has 1 valence electron. So what happens when these guys get close enough to each other, this guy really wants to, remember it has a high electron affinity, it wants electrons. This guy has a pretty low ionization energy, meaning it doesn't take a whole lot of energy to remove an electron from it. So those two things working together, when they get close to each other, this guy gives up the electron to the chlorine. The chlorine is now happy because the chlorine now has 8 electrons in its outer shell, right? It has 8 valence electrons, which makes it stable. It feels like a noble gas. It lowers its energy having that full shell. So it's accomplished what it wants to accomplish. Now the process of doing that has made it negatively charged. Okay? Sodium, on the other hand, when it lost that one in that third energy level, this third ring, when it lost that electron, now it doesn't have any in that third energy, so its greatest or highest energy level is now the second energy level, which is completely filled. 1, 2, 3, 4, 5, 6, 7, 8. So it also feels like a noble gas. It's become more stable because its outer shell is filled. It's lowered its energy, but in the process of doing that, it's become a cation, a positively charged ion, right? So when this happens, obviously in order for this to happen, these two atoms would have to be close enough for them to feel the attraction of that electron and them to swap that electrons. And then immediately when that happens and they swap the electron, and this guy takes ownership of the electron and this guy loses ownership of the electron, they're now positively and negatively charged. And then because of that opposite charge, they're then attracted to each other. So they bond together, and this type of bond, where the bonding is the result of a transfer of an electron, okay, when each of the atoms are actually charged, one positively and one negatively, and they're attracted they're attracted to each other, or bonded to each other because of that opposite charge. They are that's considered ionic bonding. So this is a picture of the formation of an ionic bond. Okay, starting out with 2 atoms, and then you have 2 ions, and of course these 2 ions being opposite charge then bond together. An ionic bond sounds simple enough. Ionic bonding is the bond between 2 ions. Right? Try this again. Covalent bonds. Let me make sure I didn't skip one. Yeah, okay. So covalent or molecular, like I said earlier, bonds. These are bonds that result from the sharing of electrons. So ionic bonding is the result of a transfer of electron from one atom to the other, each of them then getting a charge and then being attracted to each other, right? Covalent bonds is the result of sharing electron between a pair of atoms. So this atom and this atom get around each other. Neither one of them want to give up the electrons to the other, but they realize that, hey, if we just share these electrons, these 2 electrons or these 4 electrons, then we can both get what we want. We both want 8 at the end of the day. Everybody wants 8 valence electrons except for helium, which is completely happy with its 2, and then hydrogen right before helium just has 1, and it really just wants 1 more. So hydrogen and helium, they're good with just having 2 electrons, right? Everybody else wants that 8. So if they can get that 8, then even if it's through sharing, they're completely content and happy with that. So that's what's happening with covalent bonding, is they're sharing electrons, right? Note that the electrons are always shared in pairs. So that's why I said, hey, if they share these 2 or these 4 or even these 6, right, they're always shared in pairs. You've probably done some stuff with bonding before, but each bond, and we'll get into this when we do the little structures in a day or two. When we get into the bonds, when we draw a line for a bond, that, you know, if I draw this line for this bond, that bond actually represents 2 electrons, right? So sometimes you'll see them put like an electron like on each end just to show you that there's a pair of electrons. That line represents a pair of electrons. Each bond is a pair, okay? And the reason they tend to share electrons would be because of the high electronegativity. This tends to happen with nonmetals. When nonmetals bond with other nonmetals, you tend to end up with the sharing of electrons that take place. So you have a covalent bond. So if you have a metal bonding with a nonmetal, then you're probably going to have an ionic bond there, okay? But if you have 2 nonmetals bonding together, then you have a covalent bond, okay? This is just a picture of that sharing process where you kind of get to see it's, and now if you have a printed package, you're not going to be able to see the colors here. You might see a slightly different shading, I don't know. But carbon has 4 valence electrons. If you look on your periodic table, carbon would be in group 14, which means it has 4 valence electrons. So these blue electrons here are the ones that carbon is bringing to the table, okay? And then hydrogen just has 1 electron period, but that would be 1 valence electron. So this hydrogen is bringing this electron to the table, this hydrogen is bringing this electron, this hydrogen is bringing this one, this hydrogen is bringing this one, right? So carbon would not be really, it wouldn't be interested in sharing an electron with just this 1 hydrogen alone if these other 3 didn't exist, because that's not really helping it out. What carbon needs is 4 more electrons. It has 4, it needs 4 more, right? So it's not really interested in making this hydrogen happy by giving it the 1 that it wants. It needs 4 hydrogens together to all say, okay, yeah. The carbon would then make a deal to share an electron with each of the 4, and of course each of the hydrogens would be happy because they got the 2 that they want, right? And then carbon is happy because once it shares with all 4 of them, it gets the 8 that it wants. 2, 4, 6, and 8. So we have a single bond between each of these. So, but once again, they're sharing of electrons. They are not. There's not a give and a take. Hydrogen is not positively charged and carbon negatively charged or any of that stuff. They are sharing the electron. Now, there may be enough difference in the electronegativities between these 2 guys for them to be polar, which we'll talk about in a little bit, but they are definitely sharing. Remember, electronegativity we defined as the ability for an atom to attract an electron in a chemical bond, right? So how great that electronegativity is determines, the difference in the electronegativity, I should say, determines how equal this sharing is. So if they had the exact same electronegativities, then they would be equally sharing. The electrons would spend the exact same amount of time with both of them. But if there was a difference in electronegativity, which there's a little bit of a difference, but not much, between these 2 guys. If there's a difference in electronegativity, then there would be a slightly unequal sharing of the electrons. So the electrons would spend a little bit more time around the carbons than they would around the hydrogen in this case, but just barely. All right, more about electronegativity and bonding. So once again, what is electronegativity? It is the ability of an atom to attract an electron inside of a chemical compound. So 2 atoms are bonded together, right? Which one is more attracted to the electrons? Which one does the electron spend more time with? Okay? Bonding between atoms
of different elements is rarely purely ionic or purely covalent, due to the electronegativity of the elements involved here. So, can I turn like this? That's good. All right. So what we're saying is it's not a one or the other kind of thing. There's a gray area. It's not like, well, this guy's ionic or it's a covalent bond. It's either ionic bond or it's covalent bond. It's got to be one or the other. And then if it's either 100% ionic or 100% covalent, it doesn't actually work like that. What we really have going on most of the time is it's like a sliding scale from 100% covalent, and then on this end you have 100% ionic, and it's just gradually kind of slides from one to the other. So you can have bonds that is mostly covalent, but not 100% covalent. It's more covalent than it is ionic in nature. Or you can have bonds that are on the other end that is more ionic than it is covalent. At the end of the day, we classify it and we give it a title, but you can have two bonds that are both ionic, but one is more ionic in nature than the other one because there's a greater difference in the electronegativities in that case. Does that make sense? Hopefully. You'll see when we do a few examples here. You'll get what I'm talking about. Okay? The type of bond is determined by finding the difference in the electronegativities of the atoms that are involved. So we talked about that. I've kind of mentioned that. Let's look at a couple of examples of that. So here is this sliding scale that I'm talking about. You can find this in your textbook. So nonpolar would be a 0% ionic character. So this scale is saying from 0% ionic to 100% ionic. Okay, which 0% ionic, on the flip side, would mean that it is a covalent bond. Remember, ionic means that they've transferred electrons, transfer of ownership. The electron went from one atom to the other atom, and now they're positively and negatively charged, and they're attracted because of that opposite charge. Covalent just means they're sharing the electrons. Okay, so this would be 100% covalent. This would be 0% covalent, but it's always described in terms of ionic character here. Okay, so you go from being covalent to up here you're ionic. Now you can see here that the covalent's actually broken down into two categories. Okay, so we can classify the bonds, covalent bonds, in two different ways. We say that they're non-polar covalent, which means that they're like closer to 100% covalent, or they are polar covalent, which means they still are what we would classify as a covalent bond, but they are more ionic than the non-polar. Okay, they act a little bit more ionic than the others. Okay, and it's right here about the 50% mark that we then begin determining something to be ionic. So if it is more ionic than not, then we call it an ionic bond, even though it's not necessarily 100% ionic. Rarely is something 100% ionic. Okay, if it's less than 50% ionic in character, then we consider it to be more covalent, right? So it's a covalent bond. All right. These numbers over here tell us the differences in electronegativity. So these are the numbers that we're going to go by. Let me just say, if you get online and you look or you read in other textbooks or you watch other videos, these numbers may vary a little bit. It might not be exactly here, because this will always be 0 right here. But sometimes they'll say, they might say use 0.5 instead of 0.3. Right here, they may say around 2 instead of 1.7. So it's still basically the same, but that number may shift a little bit. Just for consistency for us, we're going to use these numbers, 0, 0.3, 1.7, and then the top really doesn't matter, 3.3. Okay? So when we take two atoms that are bonded together and we find their electronegativities, which I have, if you have a packet, then I gave you one of these. If you don't have a packet, then I've shared this off the Google Drive, so you can get one of these and you can look at it, or you can print it out at home if you want to, whatever. But all it is, this is a periodic table. You can always also find this in the textbook, back in chapter 4, at the end of chapter 4. Let me see. Hold on a second. I'll tell you exactly what page. It's around page 170, I believe. 161. 161 in the textbook is the periodic table with all these, the red numbers here are the electronegative values, okay? This has the same numbers there. So, there's that. Alright, so when we look at the atoms and we see what their electronegativity values are, if we subtract them, we get their differences, right? So if their differences is from 0 to 0.3, then we would say, okay, that is a non-polar covalent bond, okay? If when we subtract them, we see the differences is anywhere from 0.3 up to 1.7, we would say, hey, that is a polar covalent bond. And then if it's anything above 1.7, we'd say it's ionic. So looking at examples here, we got sodium chloride, NaCl. If you look, you'll find that sodium is 0.9, and then chlorine is 3.0. Okay, now why do they put the 3.0 first? Simply because it's bigger. That way you don't have to worry about getting a negative number, because the negative, if you did get it, would be irrelevant here. It's just the difference. You can think absolute value if you're a math person. So always subtract the bigger number, and then from that, the smaller number. So 3.0 minus the 1.9 gives us a difference of 2.1. So a difference of 2.1, that is above the 1.7, so that is an ionic bond. So with these two guys bond together, just like on the few slides back when we looked at it, there will be a transfer of electrons. So the electron will leave the sodium, it will go to the chlorine, they will have a positively and negatively charged atoms that will then be attracted to each other because of the opposite charge. Okay? And then we have hydrochloric acid here, HCl. Chlorine, once again, is 3.0. Hydrogen, if we look on here, hydrogen is 2.1. Okay? So 3.0 minus 2.1 gives us 0.9. So 0.9 is below the 1.7, so that means it's a covalent bond, but it's above the 0.3, so it means we would classify it as a polar covalent bond, which we'll talk more about in just a second. All right? And then Cl2, that is just two chlorine atoms bonded together. Okay? Anytime you have two atoms that are the same bond together, it's going to be nonpolar. But just to explain why, is because chlorine would be 3.0, the other chlorine would also be 3.0, so when you subtracted them, you would get 0, right? So anytime if you had O2, okay, well that's obviously nonpolar because they're going to have the same electronegativities, you're going to subtract them and get 0, okay? Sometimes you have atoms that are, let's see if I can find you an example. Like if we had selenium and sulfur that was bonded together, selenium and sulfur, one of them is 2.5, the other one is 2.4. So when you subtract those two, you would just get 0.1. 2.5 minus 2.4 is 0.1. Which one is it? Yeah. The sulfur is 2.5. The selenium is 2.4. So when I subtract them, I just get this 0.1, right? So this would also be when selenium and sulfur were bonded together, this would also be a non-polar covalent bond. Okay? All right. Does that make sense? Let's look at. Let me real quick. I'll do a couple more examples. So if we have calcium oxide, right? CaO, calcium oxide. If you look, oxygen is 3.5. The nonmetal is going, because it's on the right of the periodic table, it's going to have a higher electronegativity. Remember the periodic table, the trend for electronegativities was to increase as you move towards fluorine, right? So I'm going to start with this one. It's 3.5, right? And then from that, calcium is way over here on the other side, so it's going to be much less. Calcium is 1.0, all right? So when I subtract these two guys, 3.5 minus 1.0 gives me 2.5. So 2.5 is the difference, and I can look on here to see where it is, right? 2.5 is definitely above 1.7. Anything above 1.7 we would say is ionic. So this is an ionic compound right here. When these guys bond together, there would be a transfer of an electron that would take place. All right. Another hint that this is an ionic bond is it is a metal with a non-metal. Okay. If you have a metal, it's going to be an ionic bond. Okay. If you got a metal bonded with a non-metal, it's going to be an ionic bond. Okay. And the only other case, if you had metallic bonding, is metals bonded with other metals. Okay. If you have metals bonded with non-metals, then you're looking at an ionic bond. okay? Two nonmetals bonding together, you're looking at a covalent bond. So here, metal, nonmetal, it's ionic. This hydrogen, remember, even though it's on the left, it is a nonmetal. So nonmetal and nonmetal is polar covalent, and then of course two nonmetals, polar covalent. Okay? How about this? We look at NO2, nitrogen dioxide. Okay, so if we don't really have to worry about the two there, just what the electronegativities of the element is. Okay, so oxygen once again is 3.5, and then nitrogen, if you look on here, all right, I know you can't read this, but I'm just reminding you where to get this, page 161 of your textbook, or look in the sheets that I've sent out to you on Google Classroom. You can find it there. Nitrogen is 3.0. So 3.5 minus 3.0 gives me 0.5. 0.5 would be just barely above this 0.3 right here. So we would consider this guy to be polar covalent. Okay? Polar covalent. If you need a moment, if I'm talking too fast, you need a moment to think, of course, you can hit the pause button, right? Okay, so just to get into this a little bit more about the details, the difference in electronegativity in the bond. The difference in electronegativity, if it's ionic, if it's greater than or equal to 1.7. So upon the occasion that when you subtract the two electronegative values and it's exactly 1.7, we're going to go ahead and go up and say that's ionic. Okay, so if it's 1.7 or anything greater than 1.7, we're going to say it's ionic. Covalent is anything that is less than 1.7, but we're breaking covalent into two separate sections. We have the nonpolar and we have the polar. Okay, so nonpolar covalent bonds in which they're sharing it equally. So what does it mean for it to be nonpolar? Nonpolar means that there's not enough difference in the electronegativities to say there's really an unequal sharing of electrons. Okay, so remember when last unit when we were defining what electronegativity was, that ability to attract an electron, there could be equal sharing, but a lot of times there's unequal sharing. Okay, so this is the case where there's actually an equal sharing. So you spend just as much time with the one friend as you do with the other friend. So the difference in electronegativity being anything from 0 to 0.3, and that's less than 0.3, okay? 0 or anything less than 0.3, all right? We would say that's nonpolar. So 0 means there's really a dead equal sharing of electrons. The 0.1, 0.2, that kind of range, 0.3, that's saying that there is a slight unequal sharing of electron, but not really enough to say there's an unequal sharing of electrons. So we consider all that to be nonpolar. So covalent in general means we're sharing electrons, right? Nonpolar means there's an equal sharing of electrons, all right? Polar, on the other hand, is covalent bonds where there's an unequal sharing of electrons. So there is a big enough difference in the electronegativities that the one with the higher electronegativity is hogging the electrons to themselves, and they're spending more time around that atom than they are around the other. They're still sharing. It's not an ionic bond where there's a transfer of ownership taking place, but there's an unequal sharing that's taking place. So we will say that that's anywhere from 0.3 up to 1.7. Now, just like we said, the 1.7, we're going to round up. We're going to do the same thing for 0.3. If you subtract and you get a difference of, let me see if I can find an example, bromine and iodine. If bromine and iodine were ever to hook up, one of them's 2.8, the other one's 2.5. So if we subtract that 2.8 minus the 2.5, you're going to get 0.3. So what we're going to say, if it's right on that 0.3, we're just going to go ahead and round up and just say, hey, that's polar. Okay? So anything equal to 0.3 all the way up to 1.7, not including 1.7, would be considered to be polar. All right? So if it's right on 0.3, we're going up. If I go back, what I'm talking about going up is just this kind of picture. So if it's right on 0.7, we're going up to ionic. If it's right on 0.3, we're going to go up to polar. Does that make sense? Okay. All right, so this just kind of gives you a picture of what we're talking about with this difference in electronegativity. That's what this little symbol means. This is the difference in electronegativity. So if it's purely covalent, okay, that means it's non-polar. If it's purely covalent, then we have two atoms that are equally sharing the electrons. A lot of times they're going to be the same two atoms bonded together like we have with chlorine and chlorine right here. And they are splitting the sharing of electrons 50-50, okay? And then we have polar covalent, which means that there is an unequal sharing of electrons. Here, they're sharing the electrons equally, however many they're sharing. In the case of these two chlorines, they would just be sharing 2 electrons, and they would be sharing them equally. So they would be spending as much time around one atom as the other. They would be just as close to one as the other, okay? When we get to a polar situation, you're going to have a great enough difference in electronegativity that they're not equally sharing the electrons, okay? Now, that has nothing to do with the size of these things. This hydrogen looks like a pimple on the chlorine. That's simply because hydrogen atoms are much smaller than chlorine atoms are. So that's why they have it drawn like this, okay? That's not what, don't get confused by that, okay? What we're talking about is when this hydrogen atom, regardless of its size, and this chlorine atom, regardless of its size, there's a big enough difference in electronegativity. We talked about that a while ago. We said that chlorine was 3, right? Chlorine is 3, and the hydrogen we said was 2.1. So when you subtract them, you get 0.9. Well, that is polar. Okay? Because it's between the 0.3 and the 1.7. Okay? That is definitely in the polar range. Okay? Which means that the one with the greater electronegativity, chlorine, help you out here. This was the chlorine. That was the hydrogen. Okay? The chlorine, the one with the greater electronegativity, is going to be pulling the electrons in closer to it. The hydrogen, the one that had the lower electronegativity, is not going to have that same ability to attract the electrons. So the electrons are still shared, but further away from it. Okay? This creates what we call a dipole. We'll talk more about a dipole later. Okay? This is the idea of polarity. Okay? If you think about magnets, and if you think about the term polar and what the term polar means, you probably think about magnets, or either like North Pole, South Pole of like the Earth, or whatever, okay, which is, Earth's just like a big magnetic field, and that's why we got a North Pole and South Pole, okay? But if you think about magnets, we can take a magnet, one end of the magnet will be positive, the other end of the magnet will be negative, right? So if you take two magnets and you try to put them together, you know how like sometimes you can't get them to go together, they're repelling each other, but if you will flip the magnet around, then they'll stick together, right? That's because you were trying to put two negative sides together or two positive sides together, and it didn't work. But when you flipped it, and you got a positive and negative together, then they would stick together, right? So what's happening here is the same sort of thing. Inside of this molecule, all right, this hydrogen and this chlorine bonding together, the electrons are spending more time around the chlorine, which means the chlorine is kind of negative. It's not like a full -1 charge like we get over here because it's now gained a full electron, but it is kind of negative because the electrons are there. So it's a partial negative, okay? So you get a partial negative symbolized by this delta minus, and then hydrogen as a result of that would then have a partial positive symbolized by this delta plus, okay? So the hydrogen is kind of positive, not like a full positive like this guy is, okay, because it's lost the electron, but partial positive, partial negative. Anytime you have a polar bond, okay, that is a covalent bond where they're sharing electrons but they're not sharing it equal, you're going to have this dipole where one end of the molecule is partial positive, and then the other end of the molecule is partial negative, okay? And then we got ionic bonds where there's been a transfer of electrons. So the transfer of electron, we've already kind of went into details of that, but this guy ends up with the negative, and this guy ends up with the positive, and then they're bonded to each other, stuck to each other, because there is a difference in charge, because one of them is positive charge, one of them is a negative charge, and the opposites attract. Okay? Summarizing all this real quick here. So covalent, nonpolar bonds. And nonpolar bonds are covalent bonds in which the bonding electrons are shared equally, keyword equally, by the bonded atoms, and it results from a balanced distribution of electrical charge. So there's a balanced distribution of charge. In other words, you don't end up with one end being positive, one end being negative, because there's a balanced distribution of charge. Okay? Equally shared electrons results in a balanced distribution of charge. We know that that's anywhere between 0 and 0.5 and 5% ionic in character. In terms of the difference in their electronegativities, anywhere from 0 to 0.3. Okay? And then covalent bonds. Covalent bonds are polar bonds, once again. Polar bonds are covalent. Covalent bonds can be polar. They can also be non-polar. I'm saying that backwards. Polar bonds are covalent bonds in which atoms are shared unequally. They're still sharing, but it's an unequal sharing, meaning that they have an uneven distribution of charge. So because there's an unequal sharing, that means there's an unequal distribution of charge, and you end up with that partial positive on one end, partial negative on the other end. Okay? Polar bonds tend to create atoms with partial positive and partial negatives, like we just said. And in terms of ionic character, they're anywhere from 5 to 50% ionic character. Less than 50%, we're saying it's covalent, right? And in terms of the difference in their electronegativities, then we're saying anything you get from 0.3 all the way up to, but not including 1.7, we would say is a covalent bond. Okay? All right. Excellent.